useful
Yeah,
to
just considering.
Yeah.
Should I introduce myself again? Hi, I'm Štěpán. I'm a third-year PhD student at Imperial College in London, and I work on quantum algorithms for simulation of quantum systems, and specifically on quantum Gibbs sampling. So today I will be talking about dissipative quantum algorithms for thermal state preparation and their so-called mixing times. And so this will be based on shared work with my supervisor, Roberto, and also Mario Berta, who is currently in Aachen at RWTH in Germany, and our shared postdoc, Richard. Okay, so let me start by briefly motivating this talk and setting it up. So the problem we'll be talking about is quantum Gibbs state preparation, which is very simple to describe. If you are given a Hamiltonian H and an inverse temperature beta, you want to prepare the equilibrium thermal state, sigma beta, given by this normalized exponential. Now, these states are fundamental throughout nature. They are necessary for understanding molecules, they are necessary for designing novel materials, but they also have applications beyond physics and chemistry to, for example, quantum optimization and quantum machine learning with models like quantum Boltzmann machines. So it's a fundamental task to be able to prepare them and understand them. However, one which is also in general classically exponentially difficult. And clever heuristic methods like quantum Monte Carlo still work only in some regimes and struggle, for example, with fermions because of the sign problem. And tensor network methods only work up to some system sizes. And so it seems like a good candidate of problem where we could expect quantum computers to be advantageous. And this will be also motivated by recent excitement in the field in the past 3 years, because there has been development of these novel quantum Gibbs samplers, which combine natural thermalization with efficient algorithmic Markov chain Monte Carlo methods. Now, this was introduced by a seminal work from Anthony Chen back in 2023. And I will explain these algorithms in a minute. But before that, let me just set up this talk. So it will be basically divided into 3 parts. In the first part, I would review these algorithms, which will be then based on algorithmic open system dynamics generated by some Lindbladian, which will converge towards the Gibbs state beyond. Then I will explain and discuss some techniques which are used for bounding the so-called mixing time or the convergence time of the dynamics. And finally, I will present some of our novel results for weakly interacting quantum systems. So for that, the setup will be generally that we will consider some Hamiltonian, which will be written as a perturbation of some simple non-interacting Hamiltonian. And we would solve the dynamics explicitly for the non-interacting system. And then we would argue for some sort of stability of the dynamics when we do the perturbation of the system. And specifically, one such model, which we will consider in more depth, one family of such models will be the Fermi-Hubbard model, which I'm sure most of you know, is describing spin-flow fermions on a lattice. So specifically given by this Hamiltonian, where the first part describes the hopping between nearest neighbors on the lattice, and the second part describes the on-site interaction between 2 fermions of different spins. Now, this model is widespread applications from science to modeling things like electronic properties, like for example, multi-metal insulator transition, or for understanding high-temperature superconductivity. However, it's also classically hard if you are at least in 2 dimensions and still has unknown parts in its phase diagram, like the strange metal phase. And so altogether, it serves like a standard benchmark for both classical and quantum computational techniques. And also in the past few years, there have been few indications that strongly interacting fermionic systems might be so-called non-glassy, i.e. not behaving like a spin glass, and hence potentially amenable to quantum techniques, while still remaining classically challenging because of the entanglement structure. And so again, it seems like a potential candidate for a problem which would be advantageous to do on quantum computers. Okay, so there's a setup. And so let's start by reviewing these quantum Gibbs samplers. As I've said, these will combine natural thermalization with classical algorithmic Markov chain Monte Carlo. And for that, I think it might be instructive to start in the with the classical Gibbs sampling and classical Markov chain Monte Carlo. So here the problem will be the simplified version of the quantum problem. We would be given some classical system with, let's say, n particles. So would have, let's say, 2 configurations. So we would have like 2 to the n different configurations. Each will have an associated energy, EI. And so we would understand these energies, and we would want to sample from the so-called Gibbs or Boltzmann distribution, which is given by this norm. Like the terms are these exponential, but you have to normalize it by the partition function for it to be a distribution. So in other words, we understand well, or we understand a function which is proportional to the distribution, which is this exponential, but we do not understand the constant of proportionality because that's exponentially difficult to calculate. And so for these problems, it has been observed that Markov chain Monte Carlo methods are very efficient. So what are these methods? For that, you would want to create a Markov chain, which will obey a so-called detailed balance with the probability distribution you want to sample from pi, which is in literature typically specified as this condition, pi I Pij is equal to pi j Pji, which means that the transition from like some node I outside of that node is equal to the transition, the probability mass into that node. So that specifies that the distribution pi is indeed equilibrium distribution under this Markov chain. Or it can be also characterized more, I guess, abstractly by saying that the transition matrix P is a self-adjoint operator with respect to an inner product, which is weighted by the distribution pi. And this would be more natural to then generalize to the quantum settings. And what will also be more natural is that we were to consider continuous time Markov chain, because typically Markov chains are in discrete time. You would just apply the matrix P over and over again. But since we want to characterize this by like natural formalization, we would want to use continuous time. And so we would consider a Markov chain which is generated by some generator L. And for this to be a sensible Markov chain, it needs to be, the P has to be a stochastic matrix, which can be assured if you take the generator L to have non-negative elements of the diagonal. And then the diagonal elements would be the negative sum of the rest of the row. So each row would sum up to 0. And so this will assure the transition matrix to be indeed stochastic, so it's a Markov chain. And to then ensure the detailed balance, you would need this condition that P times L would be 0, pi times L would be 0. And then the indeed dynamics generated by now the transpose of this matrix, starting in arbitrary distribution pi 0, will eventually converge to the distribution we want, because it is a unique steady state of the evolution. So that's classical Gibbs sampling. Now we want to do this quantum. So first we need the so-called quantum channel generated by some operator L to make sense, to map density matrices to density matrices. And this is characterized by completely positive and trace preserving channels, which can be, if they are generated in a continuous time fashion, the generator can be characterized by this form, which is known as the Krauss theorem or Krauss form. And it will be also called the Lindbladian. And of course, it has like 2 parts. The first one corresponds to the coherent or unitary evolution of the state. And then the second one corresponds to a dissipation, typically a dissipation of information to an environment. But here later we won't actually have any environment, but from the physical perspective, this corresponds to dissipation of information.
So here G is acting like a Hamiltonian.
In a sense, but it won't be the Hamiltonian.
It won't be the Hamiltonian.
But if you were to describe like natural formalization, like in the 70s by Davis generators, then that's the Hamiltonian. But here it won't. This is just the general form of the Lindbladian. Okay, so that's the generator. But now we want to define the detailed balance with the steady state we want. And so we want to generalize the classical one. However, when we use the inner product, then there are actually like infinitely many different inner products which simplify in the classical case to the classical ones, because we can weight the inner product from these 2 sides by the state we want, with powers being s and 1 minus s, so they add up to 1. That's because the density matrices obviously do not commute in general. And you can in fact see that with any of these products, if L would be self-adjoint with respect to them, then the steady state, the sigma state will be the steady state of the generation. That's shown on the sign. You can just consider the Lindbladian kills an identity. So the inner product with any operator A is 0. Then you can take by self-adjointness the Lindbladian on the opposite side. By definition, this inner product, you get the sigma from the identity. And just by taking Hermitian conjugate of the Lindbladian, it is formed. The Hermitian, so the Lindbladian in, let's say, the Schrödinger picture kills the Gibbs state because the inner product of any operator is 0. You get that L-dagger kills the state sigma. And there are several widely studied inner products in this family. The first one, which used to be studied in the 70s, is called GNS inner product, which is when you just put all the weighting on one side. So you just have the sigma here and nothing here. And the other widely known is when you do it symmetrically and put half and half of the weights on either side. And in fact, it has been shown that every other choice of S is in fact equivalent to the GNS inner product. And the only distinguished inner product is the KMS one with the symmetric weighting. And that's in a way that it's like a weaker notion of detailed balance. However, as we've seen, all these inner products do assure that the sigma is a steady state. And so the weaker notion will actually be better because it will give us more freedom in designing the Lindbladian such that it still has the steady state geometry. So that was the one of the breakthroughs of these algorithms that they are now focusing on the KMS inner product, which is symmetric. And here it might be instructive to note that the spectrum of this Lindbladian will then be real and non-positive. It will be real because the Lindbladian is self-adjoint with respect to an inner product. So it's a self-adjoint operator, so these properties follow. The inner product is not the standard Hilbert-Schmidt norm, it's a different inner product, but still has to have real spectrum with orthogonal eigenvectors and so on. And it's also non-positive just by the dissipative nature of Lindbladians. They will have non-positive real part of the spectrum. And so together, these two properties say that the spectrum is real and non-positive. And the highest eigenvector is the steady state sigma. And if you assure some ergodicity and so on, it will be the unique steady state. Unique state with eigenvalue 0. So if you then do evolution by this Lindbladian, it will actually be killing off any other eigenvectors except the state sigma, which will be steady in evolution. So wherever you start, the evolution will converge to sigma. Okay, so that's how we define detailed balance. But how do we actually construct a Lindbladian to have this detailed balance? Well, the construction we will be following has shown that the Lindbladian has this KMS detailed balance with state sigma, if and only if the Lindblad operators else obey this modular symmetry, where the delta here represents this conjugation by the state sigma. And the coherent term can then be solved uniquely in terms of these Lindblad operators L, this functional form. And specifically, if we take the steady state sigma to be a Gibbs state, we find that the condition on the Lindblad operators just means this modular relation between L and L-dagger. And then the form of the coherent state G will include this adjoint endomorphism of H, which is just the commutator superoperator with H.
Can I check about your delta?
Yeah.
So you're defining that as an operator which is effectively a map, and then you're taking the inverse square root of it, and that's always exists in that left.
Yeah, this is defined. This is just basically if you then put -1/2 and +1/2 here, that's there. That's very simple. This part is worse, but you can still define it just by a spectral decomposition of the operators.
It's all happily through spectrum.
Yeah, it's all defined through spectral decomposition, but indeed this is a super operator, and then you are taking a function of a super operator and then applying that to an operator.
Yeah, okay.
And then it has been shown that this condition on the L's can be, without also generality, solved by this form, where you have some function of the adjoint endomorphism of H acting on some operator. This operator can be arbitrary but Hermitian, and it will be called the jump operator. And then this function will be called the associated filter function, and it just has to obey some form of symmetry. So, for example, you can think of Q here being real function, so it will be a real even function, and then the F just has to be this even function times this exponential factor. Some form of symmetry. But if you then have these L defined in this way, they will obey this symmetry, and then you can calculate the coherent term from them, and you will get the Lindbladian, which obeys the K-means neutral balance with any state sigma you want it.
Is that a painful process? Normally.
What do you mean?
Well, okay.
Because as of now, this is just an abstract definition. I will in a minute say how you actually implement it on a quantum computer.
You like in this, it looks like you have to diagonalize the Hamiltonian to define.
Well, I define it by like diagonalization of a spectral composition, but you then don't have to do it to actually implement it.
Okay.
I will
Yeah.
explain how to implement it. This is just like abstract formalism. But then the recipe is then you will specify the set of jump operators, these A's, and their corresponding filter functions. You would prepare block encodings of the operators L's and G's, which I will explain on the next slide. And then you basically get the block encoding of the Lindbladian, and so you can implement the evolution generated by the Lindbladian. So you'd start with an arbitrary initial state from 0 and evolve it for some time t, and like in the limit of infinite time, it will converge to the steady state. The point of this evolution is, or this implementation, sorry, this construction is that the time steps are efficiently implementable with basic techniques like block encodings, Hamiltonian simulation, and linear combination of unitaries, which I will get to. And then this ensures the detailed balance. So the Lindbladian, the evolution by that Lindbladian will always converge to the steady state. And so the only remaining question is how long do you actually need to evolve it for? And this quantity will be known as the mixing time of the Lindbladian, and that's what either makes it the algorithm or breaks it, because it can range from being anywhere from logarithmic in system size to exponential in system size. And so that's what we actually will study in a minute. So the definition is just the minimal time that gets you like epsilon close to the steady state in some distance zone. Okay, so how do we implement this dynamics? Well, you might have noticed that I put these F's on top of the filter functions, kind of indicating that it might have been a Fourier transform. So you would indeed inverse the Fourier transform to write this as an integral, and you get the adjoint into the exponential. But then by Campbell lemma, the exponential adjoint endomorphism is just this conjugation by exponentials. And so this is in fact the Heisenberg time evolution of the operator A. And the point is that you can actually carry out this integration on the quantum computer numerically. So you'd assume that the filter function is sufficiently fast decaying so that you can truncate the integral at some finite values. And then you will discretize the integral with your favorite quadrature scheme, so like trapezoidal rule or something. So you'll get a sum of things. And you can actually implement the sum as a linear combination of unitaries. And you can do the time evolution by Hamiltonian simulation. So here on the bottom left is the block encoding for the Lindblad operators. So here you will first start by assuming you have the access to block encoding of the jump. Then you can do this controlled Hamiltonian simulation to do the Heisenberg time evolution of the jump. And finally, you need to do the linear combination of unitaries. So you need to just like prepare the coefficients or the square roots of the coefficients of these filter functions. Then you will do the controlled Hamiltonian simulation on this part. Then you would close up the linear combination of unitaries with adjoint of the preparation. And you will end up with then the sum on this register. There's a block encoding of the Lindblad operators. And the coherent term follows similarly, but here instead of the jump operator, we would have this sum of L daggers L. So you would first need to do a linear combination of unitaries over the L daggers, L and L daggers. So that's this part. And then you will do the same trick with the integration, that you will have some sufficiently fast decaying function, you will truncate it, and you will do a linear combination of unitaries with the time evolution. So this is the full block encoding of the coherent term G. And so these two together represent the block encoding of the Lindbladian. Okay.
All of those You need to measure the right.
You need to start what?
So you have a probability of success here. Like you
Well,
need to measure.
right, yeah. If you are doing this used by measurement, there is some probability of success, but it has been shown in the construction that like it's a constant probability and you can always boost it and so on. So the implementation is efficient.
Okay.
That's fine.
Nice.
As long as you choose the filter functions to be like sufficiently fast decay.
Mhm. And can I ask how you actually do the exponential Hamiltonian?
This is a Hamiltonian simulation. So actually in the algorithm, that's what you assume is your access to the Hamiltonian by being able to do Hamiltonian simulation. But then for a specific system, you do like trotterization or QSVD or whatever you want. You can do these things for, let's say, local Hamiltonians. So this finishes the construction. So if you have any other questions towards the construction, now is the good time. Otherwise, let's then talk about the mixing times and the techniques how we can bound them. So I'm supposed to mention that now. There are like some general techniques which can be used to bounding the mixing time because the mixing time directly is very inaccessible. But the most common technique, most like generally usable technique is to bound the spectral gap of the Lindbladian. Because if we have a lower bound on the spectral gap, then we can get an upper bound on the mixing time using a Hölder's inequality. And here just note that by spectral gap, I actually mean the gap between the highest eigenstate and the second highest eigenstate. So the highest would be the steady state, which I want. And then the second one will be minus, the eigenvalue of the second one will be the minus the gap. So that's one technique. Another technique studied in like mathematical physics literature is so-called modified log-Sobolev inequality. So I won't actually be using this one here, but just to mention it, it's a technique where you bound the relative entropy of the evolved state with respect to the steady state. If you can show that the relative entropy is decaying exponentially in time, which means that the derivative is like lower bounded by some constant multiples of the graph, then you get this following bound on the mixing time, with alpha being called like this alpha being called the log-Sobolev constant. And then there are also like plethora of like non-standard methods, which I will actually use here, like the oscillator norm. And if it's similar to the like relative entropy, if you're able to show that the oscillator norm is decaying exponentially in time, then you will also get some nice bound on the mixing time. And some of these techniques have been previously used, for example, in the high temperature regimes, where like Cambis, Daniel, and Alvaro showed that if you have some constant temperature threshold above which it's always efficient. And so our work will like philosophically kind of follow these works. But then also a nice result to mention, which has been shown about 2 months ago, is from Anthony Chen and his student, that all one-dimensional spin systems actually also thermalize efficiently. But here it's important to note that not all of these techniques are equal. The spectral gap bound, which is like the simplest, most approachable one, will give you a polynomial bound on the mixing time of the system size, at most linear, or at best linear. However, these two other techniques, the log-Sobolev inequality and the oscillator norm, if you are able to show them, you'll get actually a polylogarithmic bound on the mixing time. So at the best case, only logarithmic in the system size. And so from now on, I will refer to polynomial times as being fast mixing, while polylogarithmic times would be rapidly mixing. Okay. Then there are, several approaches how to show some of these properties. But the most common feature you want to show is locality of the Lindbladian. So to study locality of quantum system, obviously you would want to use so-called Lieb-Robinson bounds. If you don't know these are bounds on the speed of information propagation within a quantum system. So if you imagine some 2D lattice quantum system, you're doing a stem evolution by that. If you were to change something on the Hamiltonian here, there will be only a finite speed of propagation of this information, independent of the system size. So you could have like an infinite system, but this information will propagate with time with finite speed. Basically, you can show, or you can state this analytically as evolving some operator A by the full Hamiltonian, and the difference of that to the evolution by some truncated Hamiltonian to only radius r can be bounded, let's say, with like a difference can be exponentially decaying in the radius r, if you assume that the original Hamiltonian also had at most exponentially decaying interactions. So either short range or exponentially decaying, but not polynomial decaying. And if we could then get these if you have these Robinson bounds, you can show that the operators appearing on the Lindbladian will also be quasi-local exponentially decaying truncation. So
polynomial decaying into the 1 over r.
1 over r doesn't work.
Yeah. So
I think there are some Lie Robinson bounds for polynomial decay, but those would be insufficient for what I want to show. So here we actually need exponential decay or short range. And so with such a bound, you can also then show that the Lindblad operators are exponentially decaying. So if you look at the difference between the full operator and the truncated operator in radius r, it's exponentially decaying in r. And the coherent term, if you split it into local contributions, it was a sum over sides. If you split it into the constituent terms, then these will also be exponentially decaying. And so altogether, the Lindbladian will actually be a sum of exponential or quasi-local terms. And another technique which is useful in perturbative regimes, which is what I will be talking about, is understanding the strength of the perturbation of the Lindbladian in terms of the perturbation of the Hamiltonian. So you imagine you have a Hamiltonian, some non-interacting Hamiltonian A0, and you would perturb that by some strength lambda. And you would want to understand how does the Lindbladian perturb with respect to lambda. And so here we would use some standard matrix analysis methods, for example, this Duhamel's identity, to show that an observable which is evolved by the perturbed Hamiltonian and the difference with a non-perturbed Hamiltonian can be again in a spectrum norm upper bounded to be linear in the strength of the perturbation lambda. Then depending on some commutator of the interaction term with this evolved observable under the non-interacting Hamiltonian. But the important part is that this is system size independent. Again, this depends only on the strength of the perturbation lambda. And with this bound, we can then show in that the Lindblad operators. Now, if I look at the operators in the interacting Lindbladian and the non-interacting Lindbladian, then their difference will be bounded linearly in lambda. And similar to the coherent part. And so again, we get that the difference between the full Lindbladian and the non-interacting Lindbladian in some norm can be upper bounded to be linear in this coupling strength lambda. So these two properties will be used basically for any technique you want to show. But one technique I will specifically be talking about is the oscillator norm technique. And so let's, for now, for simplicity, assume we are in a Hilbert space which consists of n qubits. Then the oscillator norm on this Hilbert space would be defined for some operator O as the sum of spectral norms over these quasi-derivations, where quasi-derivation is defined in this following manner. And what it does is it basically measures how much does the observable O differ from an identity at the site I. So if O would be a multiple of the identity at that site, this will be 0. If not, then it will somehow quantify how much it is not an identity. And so the oscillator norm just sums up these local contributions. And so the usefulness of this norm is that it is defined from this local structure. However, you can use it to upper bound the distance between the global evolved state and the steady state by follows. If you take the supremum over all observables of the oscillator norm of the evolved observables, and you have this upper bound. And so then if you are able to show the exponential decay of this oscillator norm under the time evolution, then you would get these states are getting closer together at exponential speed, which is the rapid mixing. And this was for n qubit Hilbert spaces, but we'll, or the basic version, but we will adapt it to different spaces and generalize it and actually make this norm to be Hamiltonian specific to actually greatly extend its usability for showing mixing time bounds. Perhaps you can be wondering, you still need to show the exponential decay. How would you do that? Well, there's like a general approach for Lindbladians in these perturbative regimes. That you would consider the Lindbladian L, you want to show the rapid mixing. You would firstly write this as a sum of these quasi-local terms. And then you would also split the terms to be some base case Lindbladian plus the perturbation of the Lindbladian. And then for the oscillator norm technique to work, you would need the quasi-derivations to obey this relation with the base case Lindbladian. So the quasi-derivation actually after the Lindbladian term would just need to be some constant multiple of the quasi-derivation. So in some like operational functional sense, the Lindbladian or the terms of the base Lindbladian would need to be like eigen operators of the quasi-derivation. So this condition is actually very restrictive on the Lindbladian for which it applies to. But if you get this condition, then you get that the base case Lindbladian is rapidly mixing. And if you then want to extend this to the like perturbable Lindbladian, then you need to obtain these bounds from like the commutators of the quasi-derivation and the Lindbladians, and also on quasi-derivation acting on the difference of the perturbed and non-perturbed Lindbladian. You would want to bound them as linear combinations of the quasi-derivations in such a manner that if you then sum up all of the coefficients in these linear combinations, you would get like at most a constant or at most a system size independent quantity. However, this quantity will specifically depend on the coupling strength lambda. It will be a monotonically increasing function with lambda. But if you get this constant, then you actually get the exponential decay of the oscillator norm, as long as this kappa is smaller than any of these constants from the beginning. Since this will be the monotonically increasing function of lambda, this condition actually gives you some maximal value of lambda max below which this procedure will work and show the rapid mixing of the Lindbladian L. So that's the perturbative nature. You will show that it's the base case Lindbladian is rapidly mixing, and you will show that up to some constant strength perturbation of the Lindbladian, it remains rapidly mixing.
So what physical systems, or what maybe Hamiltonians have a Lindbladian, base case Lindbladian that does obey this restriction at the top?
I will get it in like 2 minutes.
Okay.
Because now I get to the results for our new results for weakly interacting systems. And so here we start with the like base case, which will be non-interacting systems. And for these, we show that all non-interacting systems are rapidly mixing. So specifically, if you take separable QDIS, so Hamilton, which is the sum of strictly local QDIS terms, or if you take free fermionic Hamiltonians, which are Hamiltonians quadratic in creation and annihilation operators, fermionic ones, or free bosonic Hamiltonians, which are again quadratic in now bosonic creation and annihilation operators. All of these will be mixing rapidly in logarithmic time. But here I need to kind of make a caveat that for bosons, which are horrible to analyze, we are able to show this only for an initial state being specific to the vacuum state, because the mixing time is like the count over all initial states. However, here we have chosen a specific one. So from an algorithm point of view, that's completely fine because we want to start with some simple state like the vacuum state. But from like mathematical physics point of view, it's then restrictive. However, I can actually tell you that it does hold for an arbitrary initial state. We haven't proved it, but someone from Mario group has, and they will have an upcoming publication on bosonic quantum Gibbs sampling, so it will be included there. Yes, but that's non-interacting systems. We don't really care about them. We care about some interacting systems. And so in some cases, we have been able to show that for weakly interacting systems, this rapid mixing or fast mixing remains. So specifically, if we do a perturbation of the QDIS systems, or if we do a perturbation of so-called non-hopping free fermions, so if we just have like this sum of basically the number of operators of each term, then if you perturb these two families with a quasi-local perturbation, then we'll find that there exists a system size independent maximal coupling strength lambda, below which the system will remain rapidly mixing within logarithmic time. And in these cases, we can actually explicitly evaluate the constant lambda max if you want to for a specific system to find exactly the parameter regime where it works. However, the result on fermions is indeed quite restrictive. And for example, the Fermi-Hubbard model I mentioned before doesn't apply to that because it has hopping. But for general perturbed fermions, we were actually able to show with a different technique that the spectral gap of the Lindbladian remains constant, and hence the system remains at least fast mixing in linear time, which still gives you an efficient algorithm. So for any like perturbed, weakly interacting QD systems and fermionic systems, we get an efficient quantum algorithm to prepare the Gibbs state. However, in the second case, in the fast mixing, the constant lambda max, it cannot be explicitly evaluated. We only implicitly know there exists value, but we can't calculate it.
And so the V here is like just a.
It's an interaction term, so that can be whatever you want, but the only restriction on that, it has to be still quasi-local. So either like nearest neighbor, next nearest neighbor, exponentially claim, something. But the point is, it can be whatever you want, but it has a coupling strength lambda, which is a constant, and we show that there is a maximal value for that, for which it works.
And presumably, you can't really do anything in the non-quasi-local cases, but is there, any intuition you've had about how that would affect the spectral gap of the latching effectively? Is that going to?
Well, the issue is if you have like long range interactions, then there's basically no notion of like topological quantum order, so you can't really understand the spectrum by like perturbing it slightly. You can do like a infinitesimal small perturbation, and it can have extensive result on the gap, because you like in this case it has to work into like thermodynamic limit of an infinite size system, and unless the perturbation is like well behaved like we have, then the perturbation, even if it's infinitesimally small, can change the spectral gap like completely.
So sublimes to all weakly molecular systems at all times.
The qubit spin ones and the fermionic ones, yes.
So
Not for bosonic ones.
it's just for each one.
Sorry?
Specific one.
I'm sorry,
Specific model. So the Hubbard model, for example, would remain.
the Hubbard model is.
Yeah.
But yeah, for we can interact in bosonic systems, we do not have a result. We only have the result for the non-interacting bosons. Okay, so that's the results. And just to briefly sketch some proof techniques. For the qubit spin systems, we have used the oscillator norm. So here, it's important to first notice that if you have a separable Hamiltonian, then the Lindbladian will also end up being separable in size. And so we would consider a diagonalization of each side separately. And then we would define these, let's say, partial quasi-derivations, so that each of these partial quasi-derivations only act non-trivially on the contribution of the observable along the eigenvector numbered by alpha. And so these would then sum up to like the full quasi-derivation, which in the qubit case will be normalized by the d not 2. And because we've defined it to like respect the eigenspectrum of the Lindbladian, we still get the main relation, which makes this work. Because it sums up to the quasi-derivation. If you define the oscillator norm with this one, it will be actually an upper bound on the original oscillator norm. So we can then continue with these like new partial quasi-derivations as before to show the rapid mixing of the like non-perturbed system A0. And because these have been defined like locally, because this is only like on-site diagonalization, so it's strictly local mapping. Then the locality will like still be preserved. The locality of these quasi-derivations will be compatible with that of the Lindbladian, and so we can still extend the result to the weakly interacting regime. So that's qubit systems. For fermionic systems, it was a bit more problematic because there, for the like non-interacting system, what we needed was to diagonalize the Hamiltonian in this like Bogoliubov transformation. So we would get different like type of fermions, but in those fermions, the system would be strictly local, and then we could define the like quasi-derivations in terms of these new Bogoliubov fermions. And then specifically, we would also need to distinguish between even and odd observables in fermions.
That Oglubo transformation, does that basically break particle number symmetries?
It breaks locality,
Okay.
which is why you end up with this. But yeah, I'll explain in a second. Right. So if we do this, we then get also quasi-derivations which obey these relations. So we can proceed with them as before, and we will get the rapid mixing of the non-interacting system. However, indeed, Bogoliubov transformation sucks, and it breaks locality. If you have one spin chain, then the Bogoliubov transformation is just a Fourier transformation, so it's highly non-local. And since then these new quasi-directions don't obey or don't respect the locality of the Lindbladian, we cannot extend the results to the weakly interacting case unless we actually didn't do any Bogoliubov transformation at all. So for systems which have already been diagonalized, which are these non-hopping fermions, we can get the rapid mixing here. But that will be bad because it doesn't include Fermi-Hubbard model, which was our original motivation and actually preceding this work. But for that, we still can show the spectral gap of the Lindbladian. And specifically, this approach would again start with the non-interacting Lindbladian, which will be quadratic in fermions in this case. And so we can actually calculate its spectrum explicitly. So we find that it has a spectral gap. And then we want to understand this topological quantum order, so that if we perturb this Lindbladian a bit, then the spectral gap it has only perturbs a bit. And specifically, there has been results on the topological quantum order for spin systems, but in 2017, I think Hastings showed that it also kind of extends to fermion systems. If you have a free fermionic Hamiltonian, then it will have a spectral gap which is stable under perturbation, i.e. that it closes at most linearly in the strength of the perturbation. And with this result, and also some technicalities like the third quantization and so on, we were actually able to show that the interacting Lindbladian remains gapped for arbitrarily weakly interacting fermionic systems. But in this case, we cannot evaluate the maximal perturbation strength. We only know implicitly that there exists system size independent on the max, but we cannot evaluate it. And because this is bound only on the spectral gap, it only shows the mixing of Lindbladian to be fast in linear time, not logarithmic.
What's the third quantization doing?
The third quantization was introduced by, I think, Prosen in 2007. It's a way of basically vectorizing Lindbladian, a super operator, into an operator, into a Hamiltonian, in such a way that it preserves the fermionic notion of locality. So he introduced it to understand the eigenspectra of quadratic Lindbladians in fermions. But we've used it like more extensively because the Hastings results on the topological quantum order is only for free fermionic Hamiltonians. But what we've shown is that the Lindbladian in the third quantization is actually just a free fermionic Hamiltonian, a different one, but it is one. And because it preserves locality, then we can study this transformed Lindbladian and shown that the spectrum of this transformation is stable under perturbation, and the spectrum is the same as the original Lindbladian. So the original Lindbladian has stable gap under perturbation. That shows only fast mixing in real time, which is still fine if you care about the algorithm, because the algorithm will in this case be like quasi-cubic. In the previous case, it would be like quasi-quadratic. So it's slightly better if it's rapidly mixing, but fast mixing is still an efficient quantum algorithm. Okay. And then we also specifically consider the Fermi-Hubbard model. And here we've noticed that we can actually take care of the strongly interacting regime of the opposite limit. Because if you look at the Hamiltonian, the interaction part is strictly local, it's only on-site interaction. So if you actually take this part to be the base case Hamiltonian, and this part to be the perturbation, then you will end up with a separable Hamiltonian and hence a separable Lindbladian. And so you can actually adapt our techniques from the separable Curie systems to fermions. And with that, we were able to show that the strongly interacting regime of Fermi-Hubbard models is also rapidly mixing. We will find that for, let's say, if you fix beta and u, then there will exist a maximal value of t, below which the system will be rapidly mixing. And in this case, we use the oscillator norm, so we can again explicitly evaluate the value of t. And so just to like pictorially show now these regimes where we can take care of the Fermi-Hubbard model. If you like fix t and then consider u versus beta, then there has been these previous results on high temperatures. So for small betas, you can take care of everything. And what we've shown is for weak interactions that there exists at each beta some value of maximal value of u where this works. But in this case, it's only we know it only implicitly. So I've shown this by the dashed line. And then for strong interactions, like around infinite size, there also exists some value of t below which it works. So we have like this regime where we can show the rapid mixing, this regime where we know fast mixing, and then high temperatures also known as rapid mixing. But this like intermediate interacting regimes still remains difficult. Unfortunately, that's the one people are interested in. Yeah, getting there.
Is there a sort of addition around, I mean, you've drawn this as a symmetric thing, but it may not be fully symmetric, but
Yes.
you know, where does that sort of the middle of that symmetry line, is it U4 or something?
No idea. But as I've said, these can be explicitly evaluated, and I'm actually in the process of calculating like explicit values where the stronger interacting regime worked. That will give us some hint, but I would expect that like the ratio of U over T would be like in thousands or something. But yeah, the like I think interesting regime people typically cite is between like values of U over T to be like 2 to 6.
Yep. 4 is where horrible phase transitions start happening. Yes.
Something else, yeah. Okay, so there's fermionic systems, but for fermions, we've also done some numerical simulations for small systems up to like 12 qubits. And so firstly here, what I'm showing is this was supposed to confirm our theory on the weakly interacting regime. So we are looking at the spectral gap and specifically how far does the spectral gap close with an interaction. So we are looking at the derivative of the spectral gap at 0. And so by our theorem, this quantity has to be uniformly upper bounded in system size. Here I'm plotting it with respect to the system size, and we indeed see that in each regime we looked at, it seems to converge. So there is an upper bound, and it indeed seems to converge quite fast with like 10 qubits. So that's the weak interacting regime. But yeah, as we talk about, people care about like this intermediate strength regime. That's one thing, which is not covered by our theory. And also our theory has quite a bad dependence of like maximal interaction strength with respect to the temperature beta. As you see here, I've shown it as decaying kind of exponentially, which it is. And so we wanted to improve both of these issues, or at least like heuristically study regimes where you want to make some heuristic choices of the algorithm where it could work for like either high beta, so low temperatures, and or intermediate strength interactions. And so we've done some different choices of the jump operators and the filter function. Specifically, we've chosen now the jumps to be, before we've chosen the jumps to be the creation and annihilation operators. Now we've chosen them to be Paulis. And so here you need to like fix the relation between Paulis and Majorana or fermions. So we've just used the Jordan-Huygens transformation for that. But if we've taken now the Paulis, and we've also chosen a different filter function. So before we are using a Gaussian filter, now we are using this like Metropolis filter function. So that's from the Metropolis Hastings algorithm, if you know. Then what we've observed is that the mixing dynamics, or that both properties I've mentioned, are behaving much better in this case. So firstly, if I'm plotting the gap with respect to the interaction strength U, or on the small system sizes, obviously. But here we see that the gap remains large for a wide interval of interaction strengths, which includes like the intermediate coupling around here. And not only that, we can actually control the width of this by changing like the support of this filter function, which I'm not showing here, but we can extend it for only like a wholly logarithmic additional cost. So we can actually take care, or seemingly take care of arbitrary potential interaction strengths here. And not only that, but I'm not showing here, but the dependence on beta also seems to improve massively. And when you increase the beta, the like magnitude of this gap does not really seem to change. Like there will be some wide complex behavior appearing here, but the like overall average magnitude will still be like of order of 1, which is extremely large. So yeah, it's quite hopeful that this algorithm would provide us potentially useful quantum advantage for interesting systems. Because yeah, one thing I might have not mentioned, the results I've shown where we can prove the efficiency are not dependent on the underlying Hamiltonian being gapped. The Hamiltonian can have phase transitions. The Lindbladian still mixes rapidly or fast. So it can maybe in some cases still work across like phase transitions in the system, which is a very cool feature of these Gibbs samples. Okay, so this is for fermions. And finally, for the bosonic systems, as I've said, that's our like weakest result. We only have a result for non-interacting bosons, because bosons are like unbounded operators in an infinite dimensional Hilbert space. So they are horrible to study. The locality also doesn't make sense because you can have like an infinite excitation at one side, and then you will get an infinite speed of information propagation and so on. It's horrible. But what we've noticed is that if we restrict our view to only Gaussian states, which are like Gibbs states or Fermi states of quadratic Hamiltonians, then we can do all the like, analysis explicitly. Because if we start in the Gaussian state, let's say the vacuum state, then an evolution by a quadratic Lindbladian will restrict us to the subspace of Gaussian states. So we'll still stay in Gaussian states. And these can be characterized by their covariance matrices and also like first moments, but let's just say covariance matrices. And for that, we can then the covariance matrix is like the matrix of 2-point correlation functions. And in these cases, we were able to show or solve the time-evolved covariance matrix explicitly. And then we were able to bound the distance between the states by the distance between their covariance matrices. And with this, we were able to directly show rapid mixing of free bosons. That is only for the non-interacting case. Yeah, that's all of okay, sorry, one more thing. An potentially interesting application of efficient quantum Gibbs state preparation is that you can then immediately evaluate the partition function corresponding to the systems. Specifically, if you were to consider the Hamiltonian at 2 different coupling strengths, lambda 1 and lambda 2, and were to measure this observable, which can be efficiently prepared with just QSBT techniques because it's just 2 exponentials, in the Gibbs state corresponding to the strength lambda 1, then the expectation value would be the ratio between the 2 different partition functions. And so then there's like a typical method how to do like an annealing schedule, because this is typically done with respect to different temperatures, but I will do it with respect to different interaction strengths. But if you start in some known partition function, then you can get an unknown partition function as like a telescoping product of these ratios. So our idea here was to start with a non-interacting partition function because we can calculate that classically efficiently, and then prepare a path between the non-interacting case and the lambda we care about, and we would calculate the partition function with lambda as this telescopic product. And the only point here is that you need to take care of like the error and so on you are making, which will end up resulting in the like steps on your path having to be of the size 1/m. So you have to do n of order n of them, and then you would have to measure each expectation value like n/epsilon² times to take care of the variance, and you would end up with like either quasi-quartic or quasi-quintic algorithm, depending on the rapid or fast mixing for the calculation of the partition function for these systems. So that's an application. And that concludes our results. So just to summarize what I talked about, I talked about dissipative quantum Gibbs sampling. However, you can do dissipative quantum Gibbs sampling. However, the end-to-end efficiency of these algorithms will depend on the convergence times of the Lindbladian. So that's what we have studied, and we have proved fast or especially we have proved rapid mixing for any non-interacting system, including including separable QDIS, free fermions, and free bosons. And then we have shown that for weakly interacting fermions and weakly interacting qubits, the systems remains either rapidly or fast mixing. And finally, we have done some numerical simulations to support our theory, as well as to identify some like better algorithm choices for specifically the Fermi-Hubbard model. Okay, that's it. Thank you for listening.
I think by the statement that even if your Hamiltonian isn't gapped, your Lindbladian is, but that's still only for Hamiltonians that are low. It needs all.
That's only for the ones I showed it.
Episodes what the
So, quasi-low Hamiltonian and weak Imperial. Actually, I'm going with one thing. Quasi-local Hamiltonians and weak perturbations. But in these cases, the Hamiltonian can still be ungapped, like even a free fermionic Hamiltonian can not have gapped. But we've shown that the Lindbladian still is either fast mixing or rapid mixing, so it still is gapped. Because, for example, for the free fermionic Hamiltonian, we've calculated that the gap of the Lindbladian depends only on like the maximal eigenvalue of the Hamiltonian, so like the maximal frequency of the oscillator. So it is not specifically dependent whether or not the Hamiltonian is gapped. There is a potential that like this outcome can be still efficient like across different phases of the Hamiltonian. But as of now, the mixing time results are like very restricted to only some regimes, like high temperatures, weakly interacting regimes, or one-dimensional systems. That's basically what's known as of now.
So the still models of transfer field models.
Transfer field, Ising model. If you in transfer field if you take like a magnetic field, if you take the magnetic field to be the base case, then there is a maximal like coupling strength to the other part of the transfer field Ising model such that it works. But it has to be of like this form. So like the quadratic term would have to be the perturbation, and the like linear term would have to be the base case. So in some regimes of expected Ising model, it will work. This applies. But in other, I cannot say.
I think you answered it already somehow, but if you can't prove rapidly or fast mixing,
It doesn't mean anything about if it is rapidly or fast mixing. This is just that we can prove it.
yeah,
But the hope is it will work
yeah,
much beyond these values.
right. Because like even if you can't prove it formally, you can
Yeah, of course. The algorithm itself has no restrictions at all. But as I said, the mixing time can range from being logarithmic to exponential. For an efficient algorithm, you need to be at most polynomial. So it can happen, it cannot, as I've shown in some simulations here-ish. Here.
yeah.
We are covering weakly interacting regimes, so our results was like around here. But we see that the spectral gap actually is much wider, and we can actually even control it.
Mhm.
So yeah, this is certainly not covered by our theory, but it seems to work here fine.
Well, U equals 0, that's a non-interacting system, and then
Yes.
I was trying to work out what that means.
Here we are considering both positive and negative views, so both like repulsive and attractive interactions. But by our theory, it has to work around 0. Doesn't matter if it's a repulsive or attractive. So like this small regime around 0 is correct theoretically, but it seems to work much further away. But obviously, this is only for small system sizes. There are some attempts like we are trying to do some simulations, and there's also another group in I think Hungary with András Gillian who are doing tensor network simulations and trying to show for larger systems that this seems to work fine. But both simulations and analytical understanding is very difficult to get, so it's very restricted as of now.